Hello, welcome to this presentation. My name is Yanhan Tang. I am a PhD candidate at TEPR CMU. I'm going to present my work on split liver transplantation. This is joint work with my advisors, Alan and Sweeter from TEPR, and two surgeons, Dr. Emily Perito and Dr. John Roberts from UCSF School of Medicine. Some background about this paper. Liver transplantation is the only viable therapy for patients with end-stage liver diseases. However, even with effort, the liver supply is well short of the demand. And as a result, patients are put on the wait list. And currently, there are more than 11,000 people waiting for the life-saving liver transplants. And more than 9% of candidates die while waiting. Obviously, this is not good. So a natural question to ask is, can we use the organs we already have more efficiently? The answer is yes. And one way to achieve that is to use split liver transplantation more often. SLT saves 2 lives using 1 donated liver. Recent study shows that SLT outcomes can be comparable to those obtained in the traditional whole liver transplantation method. In the US, more than 10% of deceased donor livers are splittable, but only 1% of them are actually being split. And the majority of splitting is done to save children's lives. This figure illustrates the anatomy of a human liver and how it can be split into 2 parts. SLT is possible because human liver cells have strong regenerative capability. The traditional method uses 1 large liver and save 1 large patient's life. With SLT, we can split the liver into 2 halves, smaller halves, and to save 2 smaller patients' lives. Therefore, SLT does not only have the potential to improve efficiency, but can also potentially improve fairness, because smaller candidates are usually more vulnerable, more disadvantaged on the liver transplant wait list. They have longer queues, longer expected wait times, and worse expected outcomes, because high quality liver donors are usually accident victims, and they tend to be larger in physical sizes. This figure confirms what we said before. We see a strong negative correlation between height and death proportions on the wait list based on real data. More specifically, in the traditional method, a candidate can receive an organ from a donor of their own size or a slightly smaller one, but never a larger one, because a larger liver will cause more complications and worse outcomes. With SLT, smaller candidates have increased access to liver transplants. And note that we don't want to overdo SLT so that large candidates have significantly reduced access to transplants. Our goal here is to reduce disparity, but not to create new disparity. Questions we study in this paper. First, how to make optimal decisions on when to use SLT. When I'm talking about optimal decisions, I'm referring to some well-established transplant objectives, such as maximizing quality-adjusted life years, improving outcomes, and minimizing patient deaths while on the wait list, reduce wait list deaths, and reduce wait times. Second, can SLT improve equity? We talk about size disparity on wait lists. How can we use SLT to reduce that disparity and improve equity? To what extent can we do that? There have been studies of liver allocation systems without SLT, and there have been papers studying the methodological models used to model liver allocation systems, such as the fluid model and the price of fairness notion. In the transplantation community, there have been retrospective reviews and technical reports on transplant center levels to reflect on their experiences with SLT. And there have been ethical discussions on when it is justified to use SLT to save smaller patients' lives. We contribute to the field by being the first one to analytically model liver transplantation with SLT, and we find the exact solutions to the complex fluid optimization problems, improving current methodology. How do we solve the problem? The liver allocation and wait list systems are incredibly complex. Think about all the patient health condition changes dynamically over the time. So we use a simplified math model, namely the fluid model, that captures the first order and the essence of the system's dynamics. And we formulate equity constraints for the problem to enforce equity expectations. And we analyze the model to find the exact optimal solution, which were believed to be from a problem which were traditionally believed to be intractable. And then we evaluate the solution based on actual data. So this is the full math problem, the fluid optimization problem. And this illustrates a single objective formulation. We can also replace it with a multi-objective formulation to balance different objectives of transplants. We have capacity and non-activity constraints, and we have fairness constraints that requires the likelihood of transplant for each patient group is no worse than some predefined fairness level. This is analogous to the Rawls max-min fairness notion. And of course, we have the ordinary differential equations that capture the fluid dynamics, the patient health conditions, and removals, additions from to and from the patient wait lists. Previous work showed that the optimal solution to the previously defined fluid model follows a dynamic index structure, but they did not give the closed form solution of the dynamic indices. Instead, they resort to heuristics in several layers of approximations. We show that we can find the explicit and exact dynamic indices. And instead of directly solving the continuous time problem with ODE constraints and searching over the entire policy space, which is of infinite dimension, we can decompose the problem into finitely many linear programs. And we only need to solve these standard linear programs to find the optimal solution. This simplification allows us to further categorize, characterize, and analyze the solution properties. Besides analytical contributions, we also conducted numerical study based on real-world data and compared our proposed fluid optimal policy against 4 other benchmarks, notably the fuel speed sickest first policy, which is an approximation of the current US policy. Results show that if we stick to the current sickest first allocation priority rule, but we split all spittle livers, we can expect an 8 to 11% of utility increase, given that 10 to 15% of livers are splittable. Besides utility improvement, we can also improve equity by simply using SLT without changing the sickest first priority rule. And we see from this figure, there are a lower waitlist death rate for smaller patient groups and very small negative impacts on larger patients. And if we compare the fluid optimal policy against all other benchmarks on different predefined equity levels, we see that the optimal allocation policies, their utility values decrease slightly as we impose a higher equity level. And this means there is moderate price of fairness for those optimal allocation policies. That means not sickest first, but giving organs to those who are likely to give the best outcomes. Then there's a moderate price of fairness. But interestingly, for those sickest first policies, namely the red and purple bars, we see a benefit of fairness. And that can be explained by the fact that sickest first policy is so far from optimal when we're thinking about outcomes. And by forcing a policy to deviate from sickest first, we actually have better outcomes. And here we show a multi-objective functional value, which combined outcome and waitlist deaths. So to conclude, SLT can significantly improve both efficiency and equity. In the UK, all split believers are being split. Probably the US should do the same. And we explored other definitions of equity in our paper. We have a separate paper that studies the medical learning in labor allocation. We believe that more empirical projects investigating the benefits of SLT will be helpful in generating more discussions among the clinical audience and potentially lead to the actual SLT expansion in this country. Well, that's all for my presentation. Feel free to email me if you have any questions. Thank you for your interest and for your attention. Take care.